this example, we are told the probability of A is 0.4, the probability of B is 0.35, and the probability of the intersection of both of these events is exactly 0. So right away, if we recognize that the probability of the intersection of these events is 0, then of course there can be no overlap of these two events, which means we're dealing with mutually exclusive events. So I'm going to use a Venn diagram like this one, just to make that really clear that there is no possible intersection of the two events. If you want to overlap your circles, that's fine as well. Just make sure you put a 0, of course, in your intersection of the two events. So since we're dealing with mutually exclusive events here, that actually makes things a little bit easier. We don't have to worry about an overlap, so we can actually just put the probabilities that we were given directly into our Venn diagram. Since our A only is simply just the A circle in a Venn diagram with mutually exclusive events, and then the 0.35, of course, is completely separate from A as well. So there it is. We can put our two probabilities right into those two circles in our Venn. And also doing a little bit of an inventory here, we realize that those two probabilities only add 0.75, so we're missing 0.25 of our sample space. So we got to make sure we put a 0.25 outside of both of those circles to have our entire sample space accounted for. And of course, all our probabilities adding to 100%, or the decimal representation of 1. So now we can have a look at letter A. And letter A is saying, are these events independent? Explain. So if you know you're dealing with mutually exclusive events, you could say something like, mutually exclusive events are always dependent. That would work for me. Probably most people. I think you're really clear that you know these are dependent events, and you are actually explaining that. But I think I'll be a little bit more predictable here as well, although that is completely fine by my estimation as an answer to letter A. But I think we'll use the probability of the intersection of independent events. Remember, the definition of independence is that we should be able to multiply those two probabilities in isolation. And if we get the actual correct intersection, then that's proof that we are dealing with independence or independent events. And it won't take long for you to realize that this can't possibly occur, since the probability of our intersection is 0. Then of course, when we start multiplying 0.4 and 0.35 together, that's not going to give us 0. It gives us, I guess, incidentally, 0.14. That's not really that important here to realize that, of course, that is not equal to, I'll just keep going straight across. This is not equal to 0. So, of course, that is evidence that we have dependent events. And the reason I said it's not equal to 0, because, of course, that was the given information here. That's what our probability of our overlap or intersection should have been, which we did not get from simply multiplying the two probabilities together in isolation. So that's letter A. And now for letter B, we're being asked to determine the union of both of these events. So if we use our Venn diagram, again, sitting in front of us, the union of these events, of course, just the two numbers added up, or I guess the numbers in the circles added together. And since there's no overlap, we don't have to worry about counting the overlap more than once. So if you can read that right from your Venn and say the answer is 0.4 plus 0.75, or of course 0.75, that works as well, and I think I will do that. That would be enough evidence. Just make sure you're correct, because without showing any work, you're not going to get any part marks. And just maybe demystify our formulas a little bit more, and make sure you understand our so-called rule of sum. That if we're dealing with the union of two events, I should say the probability of the union of two events, that's going to be the probability of the first event, now plus the probability of the second event, and make sure you don't, I guess, use the probability of the intersection more than once in your calculation. And of course, we realize that this is actually going to be equal to 0, because we're dealing with mutually exclusive events. That's why you see a very special version of the rule of sum. It's just simply the sum of the two events, if, of course, you're dealing with mutually exclusive events. So I can say this probability of this union is simply 0.4 plus 0.35, and I don't have to worry about counting an overlap more than once because, of course, that overlap is 0 anyway. So that means the probability of this union is simply the sum of the two individual probabilities. 0.75 is our answer, and again, that only happens as a simple sum of two probabilities when you're dealing with mutually exclusive events. The intersection is not an issue here. Okay, so letter C, just a brief mention. We were just being asked to complete the Venn diagram below, or I guess to the right in this case, and that's been done for some time, so we were actually finished of C already. So now letter D, we're being asked to determine the probability of not A and not B. And again, the Venn diagram is probably the easiest way to answer this question instead of using formulas. Since you look at that and say, okay, I have to make sure that neither event occurs, of course we are outside of both circles. The probability of us being outside of those both of those circles for a randomly chosen outcome from this sample space, of course, that 0.25. So it's actually the probability that we're not in the union of these events. And since we already know the union of the events was 0.75, then letter D has to be 0.25. Okay, so now letter E, where we're being asked to determine the probability of A, given that B has occurred. So if B has occurred, I think we can maybe focus on that B circle. Maybe just paint it here. So there's the B circle. So if we know that B circle has happened, then we ask ourselves, what's the probability that A has occurred? And of course, that probability is 0. So I think that's enough for me. And we can use a formula if we wish, but trying to get a conditional probability formula is a little bit time consuming. It's definitely not worth the hassle here. Because of course, since we're dealing with mutually exclusive events, this is an illustration of why I always say that mutually exclusive events are the most dependent events you can possibly have in probability, because once we knew that B occurred, hence the spray paint here, there's no chance that A occurs. So it's not like event B has had just a little effect on event A. It's actually precluded or prevented any chance of A having occurred. Okay, so lastly, letter F, determine the probability of A and not B. Okay, so we can actually calculate that directly from our Venn again, using what I call the checkmark approach. So since this is the intersection of two events, we have to make sure that the numbers we are choosing from our Venn are common to both of these events. So probability that A occurs is definitely that number in the A circle. And we also have to make sure that B doesn't occur. So I avoid this 0.35, because that's B, of course, has occurred in that circle. And then I could use 0.25. Or 0.4, and then with the double check mark here, we can see that 0.4 was common to both of those events. So that means our answer here is that doubly checked 0.4. So the only number in our Venn diagram that's going to be common to the event A and also the event not B, of course, is that number of 0.4. And that might be a little surprising because this is just the probability of A. So it's like this not B seems to have had no effect on the probability of A here as well. And of course, the reason for that is we're dealing with mutually exclusive events. The degree of dependence with mutually exclusive events always kind of gives you surprising answers such as this. So maybe to demystify that a little bit, let's do our AND probability here using the AND approach, or the intersection of two events, which is a product, multiply the probability of both of those events. Of course, always take some care with that second event. The probability of it occurring, you have to keep in mind that A has occurred. So this is where we need a vertical line, conditional probability of a not B, giving that A has occurred. So the easy part here is probability of A, which is 0.4. And the weird part is this second one. Probability of not B, given that A has occurred. So if we're over here in this A circle, if we know A has occurred, what's the probability that B didn't occur? And that's actually 100%. which we'll write as 1 since we're using decimals here. So the chances of B not occurring when you know A has occurred, because we're dealing with this ridiculous degree of dependence between these two mutually exclusive events, makes this a guarantee. So as soon as A has occurred, it prevents any chance of B occurring. And that's why with that multiplication of 1 there in this calculation using our formula approach, if I can get back to a white color here, we would see that this probability is just 0.4 times 1, or 0.4. So that gives you a little more insight into why this and probability of this intersection of these two events is simply the probability of A, and that's because this orange probability underlined here is actually 100% guaranteed. Okay, let's look at one more example in this video. And this example involves 3 events, A, B, and C. We're told lots of information about those 3 events. We know the probability of A, we know the probability of C, we have the probability of the union of 2 of those events, A and B, and also 2 more of those events, B and C. And that's a lot of maybe useless information at this point, but notice, keeping with the theme of this video, we're also told that A and B are mutually exclusive. So as soon as I read that, I say to myself, and this is similar to the first example, if I have a pair of mutually exclusive events, well then here's my Venn, and I'll put it right on the paper where it's clear that we have mutually exclusive events, and then that's usually a good place to start. And we sift through that given information again. We can see that I know the probability of A is 0.5. So I can fill that probability directly into that Venn diagram. I also know that the probability of the union of these 2 events is 0.9, which means this has to be 0.4, because I have to add something to 0.5 to get that union. Since there's no overlap to worry about, those 2 individual mutually exclusive probabilities there, of course, have to add to 0.9. So we now know the probability of B. And when I finally read first question here, it's saying calculate the probability of B, which tells me that I am on the right track. I think that was more or less a hint in this question. If you were really unsure of where to start, then I think once you read the first question, you probably would start looking for the probability of B. I think that would be a reasonable place to start. And then sort out the 3 pieces of information involving those 2 events. And since they're mutually exclusive, we have the probability of B. Okay, so we're getting somewhere at least. Now the next probability is B and C. So the intersection, we're looking for the probability of the intersection of B and C. And honestly, I usually always start with the multiplication of those 2 probabilities. And of course, I'm not assuming independence here because they may or may not be independent. And of course, you can see in part B in the second question, we're being asked to determine whether these events are independent. So we definitely don't want to assume that in part A. That would be wrong. So we have to figure out the probability of C given that B has occurred. And it's possible that's 0.3, but we don't have any evidence to suggest it's 0.3 right now. So assuming it's 0.3 because you're stuck is unfortunately wrong. So our standard approach with an intersection, or probability of the intersection of 2 events, relying on the multiplication of those 2 probabilities, forced us into a dead end here, unfortunately. So we have to think of another plan. How can we figure out the intersection of a pair of events? Well, the one you might not have thought to use would actually come about by looking at the union of these 2 events, which is B and C. So if I want to figure out the probability of the union of B or C, again, I'm not going to assume that these are mutually exclusive just to make my life easier. I'm going to just use the full rule of sum, which is the probability of this union is the sum of the individual probabilities, and make sure you subtract away the probability of the intersection so you don't include it twice in your calculation. And note, this is what we're looking for in the second part of question A. We need that intersection. So I'm just going to rearrange my formula here by adding the intersection to both sides and subtracting the union. And I'm basically swapping the union and the intersection in this formula. And this is another, albeit maybe sneakier way of figuring out the intersection of a pair of events. And if that didn't occur to you at first, no worries. And if you looked at the multiplication approach and ran into a dead end, well then that's fine, as long as you know that you do have another option. And here it is. So the probability of the intersection of B and C would be the probability of B, which we know already is 0.4, added on to the probability of C, which thankfully was given information. And then we need to subtract the probability of the union, which was also given information. We were told that that's 0.58, which means the intersection of B and C, or the probability of the intersection of B and C, is 0.7. Subtract 0.58, which would be 0.12, I believe. Yeah, 60 and 10. So 12%. Probability of B and C is 12%, or 0.12. Okay, so now for the second question, is determine whether B and C are independent. So how can we determine whether two events are independent if that information simply wasn't given in the question? Well, I'm sure at this point this is becoming kind of a commonplace. We use the definition of independence, that if we're trying to figure out whether B and C are independent, we can just multiply the two probabilities in isolation. I don't have to worry about any vertical lines and conditional probabilities, because right now I'm going to say, well, if these are independent events, C shouldn't care that B happened. So this is what we're going to set up. And notice if I go up and find my probabilities, I think I can remember B was 0.4, and in the given information in this question, we were told that the probability of C was 0.3. So if I put that in here, then if these are independent events and I multiply them together, then that means the probability of the overlap, or the intersection of these events, is 0.12. Now, what do I do now? Well, remember, only seconds ago did we actually do that calculation another way, relying on our rule of sum. And I guess a jumbled around or rearranged rule of sum to determine that that was actually the correct intersection. And if we just chain those two probabilities together in isolation, multiply them, we get the correct intersection. So this means, if I can get a pen here, this means that events B and C are independent. Because of course that's the correct intersection that we got in part A.